What's up, class? All right. It's the last lesson, though. Can you believe it? I mean, I got one more lesson to teach y'all, but that's like at the end of the year stuff. It's actually not about math at all. But this is the last mathematical lesson. Okay. I've waited entirely too long. I'm sitting in my garage like normal. It's like 95 degrees in here. I'm probably gonna sweat. If a little water droplet falls in this area, I apologize. Today's lesson is brought to you by Fine Point pens. Yes, fine point, ultra fine, because we got a lot of writing to do. You need a lot of room. Also, at some point, multiple colors. Get excited for that. Multiple colors. Very exciting. All right, guys. So we're doing Taylor and Maclaurin series. It's on page 77. Is actually an introduction to Taylor polynomials. Give it a read. It's kind of long. It's pretty cool. Also, I'm going to link some Khan Academy videos that I assigned a long time ago. Some of y'all have definitely watched them. Some of y'all have not. It's okay. I'm not mad. I do recommend giving them a whirl. He explains them very well, in my opinion. If you like him. If you don't like him, then don't watch him. I mean, everyone has their own opinions of Saul Khan. So feel free to give those a whirl. We are doing the notes on page 122 because we don't need to necessarily test over Taylor polynomials. We need to test over Taylor series. That's an expansion of a polynomial, okay? So we're diving into page 122 with the notes, and this example problem is actually on page 123. So you follow me along there. All right, speaker mode. This should be a bigger screen, so hopefully this YouTube video is a little bit bigger. My headphone wire is definitely gonna dangle. It's gonna dangle into the screen, so we're gonna live. All right, so on page 122, it tells you the steps. Yeah, to find a Taylor series of f of x centered at C, follow these steps. Now, big word right here. A Maclaurin series, guys. Fun fact, that's just a Taylor series where C is equal to 0. That's all it is. Taylor series where C is 0. It's a special type. So we call it Maclaurin. Where C is anything else, like if C is equal to 1 or C is equal to 2, then you call it a Taylor series. We're going to do this for this Maclaurin series or this Taylor series centered around x or centered around 0. Okay. So the first step that we're going to do is we're going to just go ahead and differentiate a bunch of times. Okay. And we are filling in a chart that has 5 derivatives. So let's take 5 derivatives. I'll race you guys. On your mark, get set, go. Man, I could have like paused the video right there and like totally mess with you guys and then like poof, ha, I win. But I didn't. But hopefully I'm talking right now, distracting you guys because I do really want to win, kind of. I almost messed up. Okay, so you found your 5 derivatives. They're all variations of cosine and sine. You gotta make sure you get your negative signs just right. And now we're gonna find those derivative values at 0. Okay. So yeah, I'll race you again. These are pretty easy. Do it with your eyes closed. Yeah, cool. Well, some variation of 1 or 0 with some negatives in there. Okay. All right, so now your Taylor polynomial, I'm going to write this as p of x. We can follow along on page 122 if you need to. It's not that bad. But yeah, here it is. Okay. So my Taylor polynomial, or p of x, is going to be f of 0. So I'm going to write this all out. F of 0 plus f prime of 0 times x plus f double prime of 0 times x squared all over 2 factorial plus f triple prime. You see what I'm saying? Hopefully you see this on the notes. Factorial all the way to the end, okay? So for mine, it's going to be p of x. And I'm using p for polynomial. It's a Taylor polynomial. I just need to use a different letter. I could have done t if I wanted to. That would be kind of cool. You like the little border I made, by the way? I'm totally distracted right now. Helps me see where I'm going. All right, anyway, sorry. Where we're going, we've got 1, right? Now, if I write this next term, it's going to be plus 0 times x. Then I'm going to get negative 1 x squared over 2 factorial, right? plus 0 times x cubed over 3 factorial. And I'm going to do everything that we got. Plus 1 x to the 4th over 4 factorial plus 0 x to the 5th over 5 factorial. So that's the expansion. We've expanded it very nicely. A couple of exciting things. Let's see how this color comes out. Multiplying by 0, like it's gone. It's gone, right? Like, do we agree we can just say it's gone? Yeah, so that one's gone, and that one's gone, right? Like, adios. So I'm going to simplify this down. I'm going to write this as p of x is equal to 1 minus, I could write that as 1/2, because 2 factorial is just 2 times 1, and 2 times 1 is, in fact, just 2, right? All right, 1/2 x squared. Yeah, I could write it that way, about 1 or 2. I don't have to. I could keep that factorial. I could keep the factorial if it makes you happy. It really doesn't matter. Plus, I'm going to definitely keep the factorial. 4 factorial is like 4 times 3, so it's like 24, but I'm kind of lazy. X to the 4th, and I got really nothing else to write. So this is the small expansion that I have here. Now, I'm going to write this as a general term, okay? A little AKA, you know, also known as, what's my rapper name in this situation? No, that's lame. I can't even pull off the hip teacher vibes right now, you guys. We just need to figure out the pattern, okay? We need to figure out the pattern. Now, first thing I notice is I have both positive and negative terms. And I know this is going to have a pattern of alternating positive and negative. Sines and cosines are going to alternate. So the first thing I'm going to do is notice we're starting at 0, and we have positive. That means we're going to start with a big old -1 to the power of n, okay? Now, a couple things to remember. These n values, this is n is equal to 0, right? I lost some terms. They are gone. This right here is n is equal to 1, and this right here is n is equal to 2. I know, right? So this is my n is equal to 0, this is my n is equal to 1, and this is my n is equal to 2. That's where we're trying to go from here, okay? You could take some time, think about it, see if you can't figure out the pattern. I'm going to fast forward a little bit. My pattern is going to be x to the 2n all over, I'll put this in parentheses, 2n factorial. Okay, so this is going to be my series written in a general notation. Okay, this is my general series notation. Oh, sorry, I'm creating a shadow. Trying not to do that. Awesome. Okay, so this is my Maclaurin series expanded here, and then this is the general series notation here. Double check it if you don't trust it. Take some time, double check it. Plug in a 0 right there. X to the 0 is 1. 2 times 0 is 0. 0 factorial is actually 1. -1 to the power of 0 is 1. So this is 1 times 1 over 1. It equals 1. Okay? Plug in a number 1. N is equal to 1. -1 to the 1 is -1. That makes it negative. X to the 2 times 1, that's going to become x squared. And then 2 times 1 factorial is just 2 factorial, right? Plug in a 2. Do you see how 2n becomes 2 times 2 is 4? Plug in a 2 makes it positive. 2 times 2 is 4. 4 factorial. It's all there. You can go through and check it out, okay? Awesome. Now, we want to now find the interval of convergence. Now, this right here, this is a bit new. New color. This is a bit new. And the way we're going to do this is we're going to do the ratio test. We're going to do the ratio test. Now, we learned about that one recently, didn't we? Not too long ago, we did a little ratio test action. All right, so let's refresh our memory. That means we need to do the limit as n approaches infinity of the second term, so n plus 1 of my series divided by the nth term. So the n plus 1 term divided by the n term, okay? That's what we're looking to do here. All right, so I'm going to take a stab at this using all of this. This is what we're using. We're going to use this guy right here and figure out our terms, okay? So I have the limit is n approaches infinity, okay? I'm going to do the absolute value because I'm going to ditch this -1 to the power of n, do the absolute value. So I'm going to get x to the 2 times n plus 1, or 2n plus 2 if I do that distribution, all over, now I got 2n, 2 times n plus 1, or 2n plus 2 factorial. Right? Times the reciprocal, right? So I'm going to get my 2n factorial all over my x to the 2n, okay? I want the limit. Now, I want the interval of convergence, right? I want it to converge. And we know the ratio test says this will converge if this limit is less than 1. So I want to find out this to be true. What values of x will make this true? That's the question I'm trying to ask myself. So let's kind of break it down a little bit. Here we go. So the x to the 2n, x to the 2n will cancel, leaving me up here, if you guys remember, with just an x squared, just an x squared. Now the bottom, it gets a little bit dicier here. So this is really 2n plus 2 times 2n plus 1 times 2n times 2n minus 1. So the 2n is once we cancel. So once we cancel there, we're good. But we still got to do the 2n plus 2 and the 2n plus 1. We got to get those out of the way first before we get the 2n. Then we get the 2n, it cancels, bada bing, bada boom. Keep it in your absolute value. And make sure you note that this is still a limit. Don't forget the fact that we're doing a limit, guys. Okay? Now, I'm doing the limit as n's go to infinity. N is the variable I care about in the limit. If it doesn't have an n, guys, we can actually like factor it out. So this x squared, I'm going to factor it out, but not just the x squared. I'm going to factor out the absolute value. I'm going to make sure I don't forget the fact that it's absolute value of x squared. Okay? Times the limit as n goes to infinity of, now I just got 1 over 2n plus 2 times 2n plus 1. And I need absolute value, don't forget that. And this all has to be less than 1. I can do this limit problem. It's a lot of stuff on the bottom and just a 1 on top. What's 1 over a giant number? 1 over a giant number is 0. 1 over a giant number is 0, okay? Now at this point, it looks weird. You're like, wait, that's all gone. 0 is definitely less than 1. Like, wait, what are we saying? You're right, 0 is absolutely less than 1. In fact, 0 is always less than 1. I'm saying, what number for x can I plug in to make this whole thing less than 1? Well, since I'm multiplying by 0 and it becomes 0 and 0 is less than 1, it doesn't actually matter the value of x. I can plug in any value of x. Sorry, I keep shaking my camera. I need to stop. I can plug in absolutely any value of x. So what we're going to say is my radius of convergence. My radius of convergence is any number, aka infinity, right? And my interval of convergence, well, it's going to be infinity in that direction and infinity in that direction. So we're going to get negative infinity to positive infinity, okay? So here we go. Our first question in the books. We have our Maclaurin, or our Taylor series. You can think of it as a Taylor series centered around 0, and our interval of convergence. Okay, cool. All right, I really hope this works. I'm gonna try pausing my Zoom video. Hopefully it doesn't stop it. And then I'm gonna erase this and write the next problem. Let's see if it works. I'm gonna pause. Voila, I'm back. And it's a new problem. And I think no time passed, which is kind of cool. I do not know if you guys can hear this. There's a helicopter flying over my house. It's been flying over my house. It's really loud. They're clearly looking for something or somebody. I hope they find them. I hope my house is fine. I live really close to the prison, by the way. So that's always a little sketchy. But you know what? It's cool, man. It's cool. I'm not worried. I'm good. All right. So this time we have the function 1 over x, okay? We want to find the Taylor series. Now, it's only titled Taylor series because we're centered not at 0, but at 1. That's fine. It just means we're going to be plugging a 1 in this column right there. Nothing else is going to change. We're literally doing the same exact steps. Let's try this out. Okay, so this is kind of more complicated to differentiate. So I want you guys to try it, and let's see who wins. It's going to be a race, okay? All right, so this is really x to the negative 1, right? If I want to write that as x to the negative 1, it might help you out, okay? Negative 1 over x squared. I'm going to get positive 2 over x cubed. Get negative 6 over x to the 4th. Positive 24 over x to the 5th. Then negative 120 over x to the 6th. Okay, so you guys can pause it if you need to and catch back up, but you should have got something like that, right? All those numbers, which that might be kind of small for y'all. Hopefully y'all can see it. You squint your eyes, really focus really hard. Oh man, the PTO just gave me an email. I don't know if y'all can see that on my screen. I think I get lunch this week. I'm pretty pumped. Teacher Appreciation Week. You're welcome, kids. I mean, you don't have to appreciate me. It's cool. I'm not one to force appreciation. Like, it's cool. If you don't like me, that's fine. All right, I'm gonna put my 1 in. Right, I'm gonna get a 1, I'm gonna get a negative 1, I'm gonna get a 2, I'm gonna get a negative 6, I'm gonna get 24, negative 120, okay? Putting this together, my polynomial, a Taylor polynomial P of x is going to be 1 minus 1 times, now instead of just x, we're gonna be doing x plus 1, x minus 1, x minus 1. All right, that's to account for that shift because we centered it, right? Plus 2, sorry, the helicopter. Y'all can't hear it. It's just so loud. Right? Okay. 2, that's my derivative number over the 2 factorial, and I got my x minus 1 squared, right? Minus, because it's subtracting, 6 over 3 factorial, 6 over 3 factorial with an x minus 1 cubed, yeah, plus 24 over 4 factorial and an x minus 1 to the 4th. I don't want to do it because I'm running out of room, but I'll do it. Minus 120 over 5 factorial. And then, of course, my x minus 1 to the 5th. Okay. Now, some of you guys may have noticed this. What is 2 factorial? I'll write down here. It's 2. What's 3 factorial? It's 6. 4 factorial, it's 24. 5 factorial, it's 120. What are you noticing about all that? You can just totally cancel all these. Like, they're, oh guys, I have the other colors. I do. You can absolutely 100% say, get out of here, I'm canceling you. Oh, this is a bright orange. This is like Tennessee orange, very bright. Awesome, okay. So that being said, I'm just looking at this pattern. I got really P of x is equal to 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus x minus 1 to the 4th. And I'm done. I don't want to do anymore. It's like the same thing over and over again. The only thing that's changing is this number right there, right? And that number corresponds to our value of n. So if I wanted to write this in its general form, well, it alternates. Do we agree? It totally alternates. So it starts positive. We start at 0. Throw a negative 1 to the power of n right at the front. Yeah. We just have this x minus 1 term. And it's to the power of n. That's x minus 1 to the power of n. That's all it is. That is 100% all it is. You can check it, plug a 0 in there, it all becomes 1. There you go. Plug a 1 in there, it becomes x minus 1 negative. Plug a 2 in there, it's x minus 1 squared positive. Plug a 3, etc., etc. You guys should be good to go with that. Cool. So this right here is our Taylor series. This is our Taylor series for the function 1 over x, okay? So now, let's do my interval of convergence. All right, so I'm gonna come over here. I'm going to erase some of this because I want the room. Are you guys cool if I erase some of this? I'm asking like I'm going to hear an answer. I'm literally like waiting for an answer. I'm in my garage by myself. I'm so crazy. Quarantine life, y'all. It gets you, it makes you real crazy. Okay. Rewind if you're confused where this came from because we had a whole thing there, but I erased it. All right. So the interval of convergence. Now, the last problem, we did the ratio test, right? The last problem, we did the ratio test. Now, what have I told you? The ratio test is not what we always use. We just used the ratio test in the last problem because it made sense, right? But this problem, I have the series of n is equal to 0 to infinity. Yeah, I got the -1 to the power of n, but I also just have this x minus 1 to the power of n. What kind of series does this look like? We use the ratio test when it's like crazy and really complicated and hard and we don't know what else to do. This guy, if you look at it, well, it's something to the power of n. It's something to the power of n. Guys, this is just a geometric series. This is a geometric series. That's all it is. Which is pretty cool. That's absolutely pretty cool. So the geometric series says if we take this value, the absolute value of our r, the absolute value of our r, if that is less than 1, if we take the absolute value of our r, that's less than 1, then we converge. Remember, this is not the interval of divergence, it's the interval of convergence. Okay, so we only want to know when we converge. If all of that was greater than 1, we diverge. So we want to know when is that true? What value of x can make that true? Well, let's solve for it. I'm going to take a big trip back to Algebra 2 world, guys. That means I'm going to look at x minus 1 is less than 1, and I'm going to look at negative x minus 1 is less than 1. That's how we work absolute value. We look at the positive side and the negative side, okay? So when I solve this, ooh, I have room and I have colors. Hold up. Should we go back to blue? I have this like baby blue. I don't know how it's going to show up. Let's try this. If I solve this, I'm going to get x is less than 2. I added that 2 right there. This one's a little bit more work. This one's a little bit more work, and that's okay. That's okay. If I divide the -1, I'm going to get x minus 1 is greater than -1. And then I can add my 1s to both sides. I'm going to get x is greater than, because we had to move the sign. Remember, you divide a negative, divide or multiply a negative over an inequality. You're going to get a switching of the signs. And that's just going to be a 0. X is greater than 0, x is less than 2. Hey, wait a minute. That's an interval, guys. That's 100% an interval, 0 to 2. 0 to 2. Okay? So there we go. That's what we have it. That's our interval of convergence. We'll call it the IOC. I mean, I know the IOC stands for International Olympic Committee, but you know what? I'm going to call it the IOC, interval of convergence. Dope. We did it, y'all. That's cool, and that's way different than the last problem. We do have to still know our series test, our converging test. So when are we going to converge? How are we going to find out when we converge? What test do we want to use, okay? All right, guys, we got one more problem. I'm going to pause this so it seems super seamless. Hang with me. All right, guys, we're back. So I want to find the Taylor series expansion of this last question. It's a normal polynomial, so we're going to make a Taylor polynomial of a polynomial. Kind of redundant, but we're going to do it anyway, just because why not, you know? So here we go. I got to start taking some derivatives. I'm only going to do 4 because, well, you can only do 4. So I'll race you guys. Ready, go. All right, so you get your 4x cubed minus 3x squared minus 2x. Then you got your 12x squared minus 6x minus 2, 24x minus 6. And if I make any mistakes, please let me know. It's 24. You could do the fifth one, but it's 0, and I don't really care. Awesome. Cool. Let's plug in a 2 for all of these. I had to do this in advance, so I didn't look like a fool, so hang with me. That's 6, 16, 34, 42, and then that's 24 because you can't really plug a 2 in, so it's just going to be 24, okay? All right, my Taylor polynomial, P of x. Oh, no, there we go. P of x is equal to 6 plus 16x minus 2 plus 34x minus 2 squared all over 2 factorial plus 42x minus 2 squared all over 3. Oh, sorry, x minus 2 cubed. Oh, good call. Thank you, class. Thank you for catching me on that one. I made a mistake. And then 24 times x minus 2 to the 4th all over 4 factorial. Okay, guys, I have not been successful in writing a general form. So I wrote the word expansion. Even though your notes does not say expansion, I haven't found it. It's not there. So I'm gonna leave it at that, okay? But I really wanna show you guys something cool. I want you to understand something why. I left my calculator in my kitchen, so give me 2 seconds. All right, I'm back. I know I just had to run to my kitchen, but I paused it so y'all don't actually know that I ran to my kitchen. So I ran to my kitchen. All right, so check this out. I'm gonna show this screen to, find it to the best of my ability. All right, so if you look, the black function that is kind of like a W, that's the function x to the 4th minus x cubed minus x squared plus 2. That's what it looks like. Now the purple function, that's our Taylor polynomial. Now, you might be thinking like, wait a minute, dude, it's like not even the same thing. Like what's going on? Like it's like way down here. We are just showing polynomials that fit the curve around specific values. Okay, so around x is equal to 2, this curve is very, very good. Look at it. It's like almost identical. It's like a giant tangent line. Oh, that's what we're getting at. It's a tangent line, but tangent lines are straight. This is like a tangent curve. It has the same exact derivative values. It has the same exact derivative values for the first 4 derivatives. So it is going to follow that curve very closely, so closely that we're not going to be able to really measure too much of the error in between the two curves. This is a really good approximation around x is equal to 2. Now, at some point, it becomes a terrible approximation, right? If I wanted to approximate it at 0, terrible. But we want to approximate at x equal to 2 because we can use the Taylor polynomial to approximate values around 2, okay? Check this out. We can do the same thing for some of these other functions that we had, right? So at the very beginning, we did the cosine one, right? So if you look, I did cosine in red. Cosine's the red function, right? And then our Taylor polynomial that we found is the blue function. Now, we were approximating that Taylor polynomial around x is equal to 0, aka a Maclaurin approximation. Now, look at that blue line. Does that blue line around 0 match that red curve very, very closely? Yeah, it does. It's really, really freaking good. Like, this is cool, man. So I want you guys to understand what we're doing. This is a Taylor approximation around x is equal to 2. So basically, we've created a polynomial that is really, really good around x is equal to 2 at approximating these values. Cool. Awesome. All right, guys, I hope that kind of makes some sense. It's not that bad. The interval of convergence is the hardest part, and that's just another extended practice of your series convergences, like your last homework was. That's just another extended practice, okay? All right, so your homework. This is gonna be homework 6.5. Homework 6.5. We are almost done. We are on the home stretch. Ooh, man, my Wi-Fi is freaking out right now. Okay, it is page 124 all. Page 124 all, okay? Doing Canvas. Cool. Awesome, guys. I hope that helps, man. I really hope I did a good job. Again, there's a lot of great resources out there if I didn't do that great of a job. And again, you can always email me. You can always swing by my office hours. I'm there. I'm there. Trust me. Every Monday, Wednesday, Friday, I sit in front of my computer from 9 to 11, just waiting. Just waiting. I'm like, yo, is anybody going to show up today? I don't know. Maybe they will. Maybe they won't. So swing on by. If you have any questions, I got you. Awesome, guys. It's been fun. Hope you guys enjoy. This is the last thing you have to learn in calculus. It's pretty cool. So, yeah, rock and roll. I'll catch y'all later. Bye.